This is a video for OCR Pure Core Mathematics, Complex Numbers 5, Complex Roots, 5.3, the nth roots of any complex number. So if we look at this equation, I've got z to the n equals w, where w is a complex number. The roots of this equation then will be the nth roots of w. If I allow z to equal r cos theta plus I sin theta, and w to equal s cos phi plus I sin phi, what I'm saying is that the modulus of z is equal to r, and the argument of z is equal to theta, and likewise the modulus of w is equal to s, and the argument of w is equal to phi. So from my equation, z to the n equals w, this is the same equation but with z in modulus argument form, powered up. Use De Moivre's theorem here to multiply up the angles, and then here I've got w in modulus argument form as well. Now this only happens when r to the n is equal to s, and when n theta is equal to phi plus 2k pi. Remember, it's phi plus any multiple of 2 pi. So this is going to give me that r is the nth root of s, and theta is equal to phi plus 2k pi all over n, and k can be any integer in the range 0 to n minus 1. That means I will get n distinct roots, and only n distinct roots, with a modulus of the nth root of the modulus of the original number, and an argument which is the argument of the original complex number, obviously modified by a multiple of 2 pi, divided by n. I want the cubic roots of minus 1 plus root 3i. That means I'm looking for the 3 cubic roots of that. And the starting point is to find the modulus and argument of this complex number. Drawing that on an Argand diagram then, if we just sketch this in, I know that that's going to be root 3 and that's going to be 1. So for the modulus of that, it's going to be the square root of 1 squared plus root 3 squared. That's 1 plus 3 inside there, so it's root 4, which is going to be 2. And the argument is going to be this angle here. I know from this right angle triangle that this is pi by 3, so this is 2 pi by 3. So the modulus of minus 1 plus root 3i is equal to 2, and the argument of that is equal to 2 pi by 3. So I'm trying to solve z cubed is equal to minus 1 plus root 3i. If I think of z as being r cos theta plus I sin theta, I'm going to get r cubed cos 3 theta plus I sin 3 theta is equal to 2 cos 2 pi by 3 plus I sin 2 pi by 3. And this happens when r cubed is equal to 2 and 3 theta is equal to 2 pi by 3 plus any multiple of 2 pi. So I'm going to get that r is the cube root of 2 and theta is 2 pi by 3 plus 2k pi all over 3. And this means that theta can take values of 2 pi by 9, or 8 pi by 9, or 14 pi by 9. And if I want to get my cube roots, if I want them in x plus iy form, I would just plug in this modulus and this argument into the standard form. So I'd get something like cube root of 2 cos 2 pi by 9 plus I sine 2 pi by 9. So there's that working tidied up for you. There's the modulus of our complex number and its argument. And there's the equation written up with z in mod arg form and our complex number in modulus argument form. There's my values for r and for theta. And so if I look at the values for k, that gives me those values for theta, and therefore these values for my final result. There's those roots represented on an Argand diagram. So this one has a theta value of 2 pi by 9. This one has theta is 8 pi by 9. And this one has theta is 14 pi by 9. The radius of that circle is about 1.26, which is the cube root of 2. Let's have a look at a plot for the nth roots of any complex number. This example is based on a complex number 1 plus 2i, and there are 3 cube roots here, power 3 cube roots here. There's the first one, there's the second one, there's the third, and they're evenly spaced around this circle. And this circle has a radius of about 1.3. If I up the power to 4, you can see the radius of the circle is reduced slightly. I'm now doing the 4th root of the modulus of 1 plus 2i, and I get 4 roots around the circle, again evenly spaced. Push that up to 8, and again I get 8 roots evenly spaced around the circle, and the radius of the circle has come down even further. So our technique is to find the modulus and argument of the complex number that we're finding the root of, and then we find the nth root of its modulus. That gives us the circle for each of these roots, and we find 1/nth of its argument plus some multiple of 2 pi by n. The next video in this sequence is 5.4, solving equations.